Hello, my name is Gunwant purbia and I'm from group 316. My topic is the conformation of the polypeptide chain. To understand the protein structure, it is necessary to consider the possible conformation of the polypeptide chain. These conformations are primarily determined by the structure of the peptide bond like CO and NH. The structure of the peptide unit established by the means of the X-ray analysis of the peptide and the related components that are given in table 1.4 like this, and the full extension chain without deformation of the valence angles and the change of the bond length has trans conformation with the zero values of the rotational angles like AB and C. As you can see the like angles AB and C. Such a conformation is not, however, the most stable. The hydrogen atom of imine group NH form hydrogen bond with the oxygen atom of the carboxyl group. In order to find the most stable conformation of the polypeptide chain, it is necessary to minimize its total energy, including the energy of the intramolecular hydrogen bond. Two scientists like Brown and Corney have found the most stable configuration of the polypeptide chain on the basis of data obtained on the X-ray diffraction studies and the consideration of the tight packing of chain with the maximum number of the hydrogen bond. There are three such conformations. The first of all, there is the X helix. As here you can see the X helix. It is characterized by the rotation about the axis by 100 degree and displacement along the axis by 0.1 nanometer per peptide unit. Accordingly, there are 3.6 peptide units per each complete turns of helix, and the height of each turn being 0.454 nanometer. This helix is stabilized by the hydrogen bond formation between the carbon and oxygen group and of one of the peptide bond and the hydrogen and to nitrogen group of the preceding fourth peptide unit. Such bonds are formed between all the amino acid residues with the exception of the proline, which contains no NH group. The X helix may be either the right or the left-handed, as here you can see. Now the second and the third configuration with the maximum saturation of hydrogen bond parallel and the anti-parallel form. As you can see, this the parallel form and this is anti-parallel. Now these conformation are the conformation not of the single chain but of the assembly of the chain that form a platy sheet structure. These chain in beta form have no planar trans structure, as you can see. In the parallel beta form is 61 and B equal to 229, and the anti-parallel beta form has a 360 and B is 320. The hydrogen bond stabilize the fixed conformation of the polypeptide chain in the solution. The fixed conformation is commonly referred to as the secondary structure of chain. The presence of secondary structure, which is periodic, means that the chain is similar to a crystal, that alpha helix is similar to the one-dimensional and the beta form to a two-dimensional crystal. The alpha and the beta form are not only one. For example, fibrous protein have other conformation. Now this is schematic representation of the cross beta form. The conformation energy of the chain is determined by the weak interaction of the non-bounded atoms because of the planar structure of the peptide group. Of the rotational angles of the ith units are partially independent of the angles, this is 1 and a psi plus 1 of the adjacent unit. If the angles this vary within the limits allowed by the overlap of atoms of the peptide group limited by the bonds of the ith and this unit, and if the angle psi plus 1 is and vary simultaneously, then there is not such a combination of this fourth angle at which the static interaction of the ith units with the I plus 2 and the unit is possible. Therefore, the polypeptide chain has limited cooperatively the short range interaction in it, being limited to most neighbor interaction. This allow one to deal separately with conformational energies for individual amino acids. This steric map for particular residues depends substantially on the nature of its radical R, and it may be presumed that the interaction in given pair of peptide group characterized the amino acid residue that links these groups together. Ramachandran studies the dipolide glycogen L-aminine and obtained a conformational the steric map for alanine. This calculation was based on the assumption that atoms are rigid sphere having one Rayworth radii determined from the data on internuclear distance in molecular crystals. Using the potential of rigid sphere, one can eventually obtain only that allowed and forbidden region of value of this psi. This figure shows the map of alanine. This figure is the solid line denoted the region allowed at ordinary internuclear distance, and the dotted lines that those allowed at the minimum distance. As you can see the dotted lines. The map given the values of I and phi for the right and the left hand alpha helix and the parallel and the anti-parallel beta form. And for the fibrous protein collagen, analogous map have also been plotted for other residues. Naturally, as the size of radical R increase, the region of allowed values of I and phi dimensions. More rigorous calculations have been carried out with the aid of the following potential. This, and the potential URI may be taken in the form of Lambda-Jones 12-6, and the potential or the 6 expression potential. The quantity of UC characterize the Coulomb's electrostatic interaction between neighboring pair of peptide groups, which is determined by the large dipole moment amounting up to 3.7 d. The energy barrier of LV and U are found from the data obtained in the investigation of small model molecules. Eventually 2.1 is less than 2 U and 5.1 kilojoule per mole is 2.1 is the energy barrier for H3COOH, and the 5.5 for H3COL, and the U4 is less than from 6.3 kilojoule per mole. These barriers are small, much lower than those for hydrocarbons. The parameter for Lambda-Jones 12.6 potentials are listed in table, and the calculation of UC is complicated by the fact that the value of dielectric constant that appears in Coulomb's law that is unknown. As you can see, where EI and EJ are the charge on the atoms, that I and J. If there are no other atoms or molecules for the solvent, that is water, between the interacting atoms, then C is equal to 3. This value corresponds to the hydrocarbon or the genic environment. For atoms oxygen and nitrogen linked by a hydrogen bond, this use can be made of a function of U equal to Uij plus Uc, which is determined from values of hydrogen bond energy and equilibrium to OH and distance. Now this figure shows the steric map of alanine. The number on the curve indicates the value of in kilojoule per mole of the energy U, as you can see. Now thank you.